All right, so linear regression. The equation is y hat equals a plus bx. What is my a? My y-intercept. Good. And what is my b?
Your
Slope. We'll get to that in a minute, what that is. Yeah, so the interpretations, we're going to start with slope. So given a number of a slope, what does that say on your yellow paper? What is the interpretation of the slope?
For each unit increase in x, there's an approximate increase / decrease of b and y.
Oh, good. So for each unit increase in x, there is an increase / decrease of whatever your slope is, so b, in y. So what you would insert for context is, guys, stop talking. I'm recording right now. So for x, you're going to insert your context. For b, you're going to insert context, and then y, you will insert context. So every time you're increasing 1 unit, like 1 inch tall, then your y, so your weight, could be increasing or decreasing by whatever your slope is. So the next one is y-intercept. When I'm interpreting the y-intercept, that is when your x equals 0. So what does it say on that gold sheet, Eric? You read it so well last time.
Oh, I have to. Which one?
For y-intercept.
Yes. Y is a, in parentheses, y-intercept, close parentheses, when x is 0 units.
So when x is 0 units, or you could, I'm going to erase that and put is 0 units. My voice. So when x is 0 units, y is the y-intercept. So you're just saying, like, when you have studied for 0 hours, you could make a 43 on the test. That could be your y-intercept. Correlation coefficient, so my r value. This is the LSD thing. Do y'all remember that? LSD? Yeah. Probably going to get fired for putting this on a video. LSD, what does that stand for?
Linear strength direction.
Linear strength direction. So I would say there is a then linear strength direction. So you would put LSD. I'm going to put strength first. So strong, positive, linear association. Between x and y. So those are the things that you are inserting. Context. Linear always stays the same. So this is my strength. And this is my direction. So it could be strong, it could be what? Moderate or weak. It can never be negative. Well, it could be negative. That's with the direction. So it can be positive or negative. And does anyone remember the cutoffs for what values make it strong, moderate?
0.5, 0.8.
So 0.5 and 0.8. So if I have my number line, anything from -1 to -0.5 or +0.5 to +1 is considered weak. Weak. And then the next cutoff is at -0.8. 0.8. Wait, I've got this mixed up. -0.8, and then 0.8, then 0.5 and 0.5. Yeah, I'm getting this backwards. So anything from -0.5 to 0.5 is weak. Anything from 0.5 to 0.8 is considered moderate. 0.5, 0.8.
What's this number that fits in the chart?
These are like the strength. These are just what the rule is. Anything from 0.8 to 1 is strong. Anything from negative 0.8 to negative 1 is strong. So 0 to 0.5, 0 to negative 0.5, weak. 0.5 to 0.8, negative 0.5 to negative 0.8 is moderate. And then 0.8 to 1, negative 0.8 to negative 1 is considered strong. So my r squared, what is the r squared?
The code, or it's the amount explainable because of the.
Okay, so it is approximately r squared percent of the variation in y. That would be context can be explained by the LSRL between x and y. X and y would be context. Okay, so this unit right here, it's a continuation from the LSRL or linear regression, but now we're going to learn how to do an inference test with it. So things like computer output, scatter plots, all of that kind of comes back. Those interpretations that we just did are ones that you do need to memorize and have those ready for next class. But we will be learning assumptions and stuff that go along with that. So suppose we were to investigate the relationship between the first year college grade point average and then high school GPA. So we're finding the correlation between high school GPA and college GPA. So is the first year college grade point average determined solely by the high school grade point average? So what we're trying to figure out now, and that's why we would run an inference test, is now we can actually prove whether there's sufficient evidence to prove that there is a relationship or not. So now we're just taking it a step further. A relationship in which the value of y is completely determined by the value of an independent variable x is called a deterministic relationship. So that would just mean that 100% of the reason why y happens is because of x. And that's just a vocab term that you'll want to know. So deterministic relationship, the reason why y happens is solely because of x. So the reason why you have a GPA of something in college is because of x. Most things do not have a deterministic relationship because one thing does not always cause something else to happen. There are other outside factors like extraneous variables and things like that that would get in the way. So whatever you do in high school doesn't determine what you do in college. You could do better or worse in college based off of that. And a description of the relationship between two variables that are not deterministically related can be given by a probabilistic model. So there's two types, deterministic and... So this is considered the population regression line where we have alpha and we have beta, and those are Greek letters, so that has to do with the population regression line. And without random deviation and errors, all of the observed points would fall exactly on the regression line. So what's another word that we learned in the first semester that kind of is the same as an error? Not outliers. It starts with an R. No. Residual. Yes, residual. So residuals and errors are the same thing. Basically, my observed values are going to be off of the line of best fit, and that's considered an error in a sense. So not everything falls exactly on that. And does anyone remember the formula for residuals?
Oh, it's all of the ones above and then all the ones below.
Standard deviation.
Mm-mm.
Distance.
It's the distance, so we would say residual equals observed minus expected.
That's what I just meant.
That's what you meant.
Sure you did.
Remember? Or I think that we use the word predicted in this unit instead of expected. It's okay. Predicted. That's a better word. Or
Hey, mark that.
So really,
That's right.
we've been using residuals this whole past year.
we have, exactly. And also you could say actual minus predicted and remember it as like AP. So actual minus predicted.
So we did the whole thing wrong?
And that's like AP. So you can remember it as in the order of AP or old people, OP. Whichever one that you want to remember. Yeah, AP stats. So the population slope, that's my alpha. My beta would be the slope, alpha would be the y-intercept, and then error would be your residual or the distance from that. So here are heights and weights of population adult women. How much would an adult female weigh if she were 5 feet tall? So here's an example where we have taken a sample of women who are all 5 feet tall. So they all have the same X value, okay? They're all the same height, but they all weigh different things. So that's why it creates a vertical line. And so if we were to find the mean of this, that would be on the line of best fit. Because remember, and something that you do need to know is that when you have your line of best fit, the mean of your X and the mean of your Y always falls on that line. So if you don't have that memorized, you might want to write that down. Where if you have, so if I have my line of best fit and it's going through this, X bar, Y bar will always fall on your line of best fit or your LSRL. So the mean of my X's and the mean of my Y's, they're always on the line. That means they don't ever deviate from it. It always goes through that center point.
You wish you had a minus now, huh?
So if I were to, so here's my mean of my X's in the middle. If I were to calculate the errors or the residuals, what would they add up to? Does anyone remember that? Zero. So because you have some that are above and then some that are below. And that's what the mean is that they add to 0. So the assumptions of the linear regression model, these are the assumptions for your free response that we're going to do on Friday. So I'm not going to spend a lot of time here. So you don't need to write all these down today because we're going to do that more with the free response. Cool. But the first one, there's 4 of them, and they're a little lengthy to memorize. But it's okay. We'll be fine. This is the last write-up that we ever have to do. So, yes.
How many
Yeah.
total write-ups are there?
I think we have like 10 or so different kinds. So the distribution of the errors has a mean value of 0. So the first one that you write is that your mean equals 0, or the mean of your errors, which is easy to memorize. The second one is that your deviations are independent of one another. So what that means is, are some of these weights more likely than others? What would the distribution look like? So if I took a sample of 1,000 women and they were all 5 foot tall, and then I created a dot plot or I created a histogram or something, what kind of shape would that make? Like, what would the shape of my distribution be? Normal. Perfect. That was exactly the answer that I was looking for. Probably was on your PowerPoint. They are normally distributed. So at each X value, we have a normal distribution. What would you expect for the other heights? The same kind of thing. So you would have a normal distribution at every X value. It's kind of what this looks like. And then where would you expect the population regression line to be? Where do you think that it would go through?
X bar, Y bar.
Through the X bar, Y bar, through all of the means at every X value. So in the center of every normal curve. If we wanted the standard deviations of all of these, they would all be the same. So something interesting about every X value is that the standard deviations are the same, which is the last assumption. You can highlight or underline this slide and say memorize, but we're going to do more with the free response next class.
Cool. Wait, come on, what slide?
This slide. These are the 4 assumptions, yeah. So if you want to start maybe trying to memorize them, that might be good. There are 4 of them.
I'm gonna be out of town. I got you
Why would I do that?
on Friday. Can I like come in?
I'll probably record the lesson again. Yeah.
These 3.
So, listen. So this is kind of what it looks like 3D. This is what your scatter plot would look like. At every single X value, you have a vertical distribution. That's the sample of every X value. They're all normally distributed and they're all evenly spaced. So imagine a bunch of normal curves at every X value. And then the line of best fit goes through all of the means. So it goes through the center of all of the normal curves. The standard deviation is the same for each x value. So this is the formula that we're used to, y hat equals a plus bx. This is whenever we're taking a sample and we're trying to estimate the true regression line. So the difference between the one that we just did and this one is now we have an a and we have a b. On the one that we did earlier, it's y equals alpha plus beta x. So this is my population regression. And how do we know that something is population? What is the symbols are usually what?
English.
They're Greek, yeah. So in population, the symbols are normally Greek. And then in sample, they're English alphabet. So we have A and B. So this is our sample. Another difference is that we have a hat here. And what do we call that? How would I read that? Point estimate? No. It's our y hat and it's a predicted y. So it's predicted. That's what the hat means. And remember, you get points taken off if you don't put the hat. So it's our predicted y and a plus bx. We're going to use that line to try and predict the population regression line. So a good true or a good multiple choice kind of question would be trying to find the difference between these two. So don't get them mixed up, because if you have Greek letters, that's population. You have English alphabet, it is sample.
Oh, no.
So our point estimate, all of this right here, I would not say memorize. Remember how we used our formula chart and we solved for the slope and had all of those formulas on there?
No, I missed that bonus question.
Yes, you might have. So I'm going to say don't learn all of this, because this is all on the formula chart. So you can just kind of cross through all of that, because you don't need to memorize. It's all on the formula chart. Okay? And we'll go through a problem like that. So whenever you have your x star, which we're going to say in a minute, x star is your point estimate of the mean y value. So it's at the center, it's your mean y value, it is your point estimate, which is your average. It's also a prediction of the individual y value when x equals x star, kind of like a t star or z star type of thing. So there's two different ways that we can interpret what x star is, which we'll see here in a minute on a formula. It can either be the mean, like a point estimate, so the center, or it can be a prediction. So I would just circle mean and I would circle prediction. And all of this kind of stuff is more conceptual, so it's stuff that you'd see on a multiple choice type of question.
Yay.
So it could be x star, could be a mean, or it could be a prediction, and it would work in both cases. So what I want us to do right now is I want you to put your x's in list 1 and your y's in list 2. Okay, so we have all of these numbers in there. Should never say that. If I wanted to sketch a scatter plot, how would I do that in my calculator?
Put dots randomly.
Second y equals.
Second y equal. Plot off.
Plot on.
Right.
Top left.
Top right.
X list is L1. Y list is
L2.
L2. Good. And then zoom.
Yeah.
Zoom 9.
How do you get 2 lists?
9.
Well, there.
Second L1, or second 1 and second 2.
Wait, can you come over here?
Yes.
Do y'all see this?
This is what our scatter plot looks like. Just based off of that, I would say what about the correlation?
It is a positive.
Positive. Does it look strong?
Yes.
Looks pretty strong. Yeah. So we want our scatter plot to have a linear pattern. And this tells us that we have an appropriate linear model. So first thing that we draw is a scatter plot. So we have reviewed how to get a scatter plot. If I were to create a regression line, does anyone remember how to do that in our calculator?
Stat. Regression.
So I go to stat, calc, linear regression, option 8, because it's a plus bx. Then I hit calculate. Does anyone have a and b but no r and r squared?
How is it 8?
A plus bx.
Where?
Stat Calc 8. Stat Calc 8.
What's the frequency?
So if I were to interpret the slope, with every increase of one x value, so what is my x in units? Years. No, my x is years. So for every increase in 1 year, I'm increasing 245.15 grams. So that would be interpreting the slope. This would be what I would expect if I said interpret the slope. So every time you increase 1 year, the baby is increasing 245.15 grams. How would I interpret the y-intercept? How would I interpret the y-intercept?
When x is equal to 0, y.
So what would it mean when x is 0?
When mother is 0, the baby's weight is negative 1,100.
So when the baby is 0 years old, they weigh negative 1,063.45 grams. Does that make sense? Oh, when the mom is 0, I guess. When the mom is 0.
That makes more sense.
Yes. So does that make sense at all?
Yes.
No. So remember, sometimes the y-intercept does not make sense. Like when you have negative weight, when you have negative volume, things like that. Doesn't make sense. What is the point estimate for the mean weight?
3,249.95 grams.
So what it means for the point estimate, I want you to underline this and highlight it, please. Point estimate. Yes, point estimate would be the mean weight. So the mean of my x's is 18. So when you plug in 18, it's going to give you the mean y. Okay? Point estimate is just when you're plugging in the mean. So write that out in the margin. When you're plugging in the mean, so done with y'all. Stop. When you plug in the mean, you're getting a predicted y. So my point estimate is at 18, and then my y hat would be 3,249.25 grams.
Can't you not plug in a number outside of the x range that you already have?
Right, that would be extrapolating. We don't do a whole lot with that in this unit.
Sharpest attack.
So 2 ways that I interpret this. This is a predicted point, because remember you can interpret the point estimate 2 ways. It's a predicted point, so when mother is 18, they will weigh that amount. And then also it's a mean weight for all babies born to 18-year-old mothers. So it serves as a mean and it serves as a predicted value.
Wait, where do you get the mean from?
So the way that we're interpreting this point estimate is we're saying when you plug in, this is an ordered pair, like it serves as a predicted value when I plug it in. So point estimate can be a value and it can also be a mean. It serves 2 purposes. The mean of all, so I'm now saying because of this predicted line that I get, I'm now saying that this is the average for all 18-year-old mothers as well. So it's predicted for one mother. So let's say that this mother is 18 and I want to predict what the baby will weigh. I'm going to predict that number. And then also if you ask me the question, what's the average of all 18-year-old mothers' babies' weight, then I would give that number as well. So there's 2 ways to interpret this number, an average and a prediction. So a value and a mean.
How do you think
18 was the average x value.
Did they give it to us?
No, I had to find it
How?
in the calculator. Yeah.
Where? I don't see it. Where'd you find 18? Yeah, where do you find the
18,
18?
it'll either be given to you or you just find the average. Yeah. Or 1 bar stats on list 1. But sometimes it'll be given to you. Most of the time they won't make you calculate it. So the degrees of freedom for this unit, it does not calculate it for you. You have to know. We are using n-2 now. N-2. Wait, why? That's such a good question. Because now we have bivariate data. So, bivariate, 2 variables. We need 2 degrees of freedom because do you remember me explaining what degrees of freedom for n minus 1 was like? Like if I said the average of the test was an 80, 4 people made a 90, a 95, a 73, an 82. Well, that 5th person would have to be a fixed value to make the average 80. It's the same kind of thing for degrees of freedom like this, but now you have to have 2 2 degrees of freedom because you have bivariate data. So 1 for each variable that would make the average whatever you were looking for. So now it's n minus 2 because you have bivariate data or 2 variables. We're going to skip this part, skip this. You don't need to know all of this. The only part from this slide that you'll need to know is the standard deviation, or this S sub E right here. We would pronounce this as the standard deviation of errors. Good.
This PowerPoint is online.
Yeah. So it's the standard deviation of your errors. That's how I pronounce it. You don't need to know how to calculate it. You don't need a formula for it. None of that stuff. All of this right here, you don't need. All I need to know is that this is pronounced as the standard deviation of the error. So if I took all of my errors and I created a standard deviation between them, like a typical deviation, then that would be what this would be right here. So on this slide, it gives me the standard deviation of the errors. I said you don't need to know how to calculate it. So this formula right here, you don't really ever need to know. But if I give you a standard deviation of the error, this right here is the interpretation. So you would say for a particular x value, you might even want to add that into the interpretations at the bottom of that one page that we filled out, because this is a new one, standard deviation of the errors. For any particular, or for a particular x value, the typical deviation for possible y value is approximately, and then you put in your S sub E. So for any x value, at any x, the typical deviation of y is your standard deviation of errors. So about the distance that the y's deviate from each x value. Because you know how we made that graph where you had a normal curve at every single x value? It's kind of like the standard deviation at every single x value is what the S sub E is.
And this is the script for...
Uh-huh. Yes. So mother's age would be my x context. Weights of babies would be my y context. And then 205 grams would be my S sub E. And this one. This is a new one that we're learning. And observed weight of babies can be explained by the LSRL between x and y. That's another script that we have memorized, right? So then we're going to talk about the sampling distribution of the slope. So that's what our inference testing will be. We're testing the slope. And whenever we're testing the slope, we want to see if there's a relationship or not. If you have a slope of 0, that means you have no relationship. If you have a positive slope, that means you have a positive relationship. And if you have a negative slope, that would be a negative relationship. So based off of this equation that we already found right here, so weight equals negative 39.42 plus 2.85 times height, what is the true slope of the regression line for weight on height? So what is the slope? 2.85. So we would call that beta because it's a true slope. So beta represents slope. So would that mean that we have a positive or negative relationship? Positive. And that makes sense because when you are taller, you are expected to weigh more. So that makes sense to have a positive slope. We're going to skip that. We're going to skip that. Since beta is almost always unknown, so we don't ever really know the true regression line. That's what we're trying to predict, and that's why we use inference testing. It must be estimated from independently selected observations. So we use slope B. B is our sample, as opposed to beta being our population. And then that's going to give us a point estimate. So we have talked about the assumptions, and we're going to do more with that next class. Here are the 4 assumptions. That's another place in your notes that you could highlight it and say memorize, but we're going to do it next class. I just kind of want to get through the basics first. These are the 4 assumptions that we'll learn. Mean value is 0. The errors are independent of one another. You have a normal distribution. Standard deviation is the same. To verify this, we'll draw 2 different types of graphs. We already drew a scatter plot. The second one is that we're going to draw a residual plot. So let's go over how to do that really quickly. So since I've already calculated my line of best fit, I now have residuals. So if I go back to second y equals plot 1, I change my y list to be resid. Does anyone remember how to get to resid? You go to second stat resid. So it might be 8. For me, it's 9. I don't know why, but. And then you go to zoom 9. And you want your residual graph to be what?
Dots.
Dots. I want it to be randomly scattered, right?
There's a line going through dots.
That's cool.
Wait, do you make it your Y list?
So you make your y list residuals. So you want your scatter plot. You want that to be linear. And you want your residual plot, you want that to be scattered. So when I drew my residual, it looked something like this. So is this what everyone's scatter plot or residual plot kind of looks like?
Yes.
Where my x is going to be the age, maternal age, and then my y would be residual. So you would just put resid like this. So in your assumptions, you're going to draw the 2 graphs. Yeah, like that. So here is the formula for your inference test. This right here is your confidence interval formula. B equals T star SB. So B plus or minus T star SB. If you have the data, then it will do that for you when you just do a linear regression T interval, which I'm going to show you here in a minute. This formula is not on the formula chart, unfortunately, so you do have to memorize. So you might want to put memorize. It's not even in like words on the formula chart. This is nowhere to be seen.
Wait, there's words? Where?
On the back of the formula chart where it has like point estimate plus or minus. Yeah, so my point estimate is B. T star is my critical value, and then it's the standard deviation. So in your calculator, let's say I wanted to do this on my data that I have. I go to stat test, and then I do linear regression T interval. So it is stat test G. Yeah, G. Did you know that it even went that far?
Yes.
And let's say that I want to do a 90% confidence interval.
What's reggae? Reggae.
What?
Just reggae.
I don't know what you're saying. So everyone calculate a confidence interval for this data that we already have in it. Stat test G. Stat test G. It gives you the interval. So I got 159.78 to 390. It gives you the slope, which is B. It gives you degrees of freedom. It gives you your standard deviation, so that S is the same thing as SB. So it's S in your calculator. But it's SB on the formula. Gives you your y-intercept, it gives you your r squared, and it gives you your r. So it kind of gives everything there. So when you run a test, it has all the information that you would ever need. But we'll do write-ups, like I said, next class. So don't stress too much. Just knowing how to run the test. Then we are blank % confident that the true slope of your context is between blank and blank. Gonna skip that part.
Alex, you like what?
Okay, so what I want us to do now, this is our last thing. I want you to go to the page in your packet that has this computer output as like one big page. It's in your packet. Yes. No, it's in your pocket. There it is, right there. It looks like this. Right here in your pocket. You're going to label this. It's in your pocket. Next one, next one, next one. Right here. Yes. Is everyone there?
Yes.
That right there.
All right, so what we do know so far, it gives us the regression equation at the top. If it does not, which one is my y-intercept?
The constant.
The one that is constant coefficient. So it gives us the equation of the estimated regression line. This is my y-intercept, so circle the 88.796. That is my y-intercept. One way that I can tell that it's my y-intercept is because it's always next to the word constant. And then my slope is always next to the word that is my x. So in this case, or in this example, my x variable is treadmill. I think treadmill time. So your x variable will always be written right here where it says treadmill, and the number that's next to it is my slope. So y-intercept is 88, slope is negative 2.3335. Do we keep all of the decimals in computer output? Yes. Even if it goes out 10 decimal places, we still keep all of it. You don't round in computer output. This 0.5911, so the number that is next to my slope is S sub B.
Sub B.
Sub B.
S sub B.
That is the estimated standard deviation of the slope. So standard deviation of the slope. We're using that. These are the two numbers that we will use in our formulas. So when we're doing inference, the only two numbers that you'll need when we're calculating our test statistic and our confidence interval will be our slope, B, and then SB. They're always side by side. So those are the two numbers that you need when we're doing inference.
Wait, so slope is the 2?
How do you have the standard deviation?
Slope is the negative 2.3335.
How do you have the standard deviation?
That's 0.5911. It gave it to me. A long formula. But computer output will give it to you. And this S down here, 2.188, that is the standard deviation of the errors. And this is my R squared. Things that you want to cross out. You cross out the R squared adjusted. We don't need that. So if you haven't written this down, this is the standard deviation of my errors. R squared. Cross out, you never use R squared adjusted. I'm going to go back. So I'm going to go to this because I don't like the way that they have it. These right here, so what I want you, we crossed out R squared adjusted. This up here, I want you to cross out because we never need these numbers.
That's so sad.
I know. This negative 3.95 and this 0.003, this whole half of the computer output is sometimes on there. Only sometimes. Half of the time it's not on there. So it's usually just up in the air whether they include that or not. But what the negative 3.95 is, that is my test statistic. And this number, this 0.003, is my p-value. So it actually ran the test for you and you didn't have to do any work.
No.
Which was really nice. But like I said, most of the time it's not on there. It's usually cut off, and then you have to calculate those two things yourself. So those are just depending on whether they're there or not.
And those will be on the same row as like the X.
Everything above that you would cross out. This is the SS resid, this 43.097. We never use that, so you can label it, but we don't do any formulas with that. So just there to label. And that you don't need to know. So those numbers, nothing down here do you need to know except your degrees of freedom. It's the middle number, this 9. So the number that is next to residual error is your degrees of freedom. It's the middle number. So circle the number 9. That is how many degrees of freedom I have. So 2 formulas, reading this computer output before we stop today. 2 formulas up here. We have a confidence interval formula. And does anyone remember what the confidence interval formula was?
B plus or minus.
B plus or minus T star SB. So reading this computer output, if I were given this, my B is right here. So it would be negative 2.3335 plus or minus, I'm going to leave a blank for T star. We'll fill that in a minute. And then S sub B. So my T star is going to go here. I'm just going to leave that blank for now. 0.5911. So to get my T star, I'm going to do inverse T in my calculator. So let's go to that really quickly. Inverse T. Let's say we're doing a 95% confidence interval. If I were doing a 95% confidence interval, I would do inverse T of 0.975, and then I would use 9 for my degrees of freedom. And you get 2.262. So when you have computer output, you have to calculate your confidence interval on your own. You don't get to do a fancy stat test. So we're actually going to do this by hand. So negative 2.3335 minus for my negative bound, I got negative 3.67. And for my upper bound, I got negative 0.996. Zero is not contained. Good. Okay, the next formula is my test statistic formula. So how do I get this negative 3.95? Statistic. It would be T equals B over SB. So I am just dividing this negative 2.3335 over 0.5911. So try typing that in your calculator. And you end up getting 3.95 or negative 3.95, which is right here. But like I said, these two numbers may not always be on the computer output. They usually leave those off. So let's say that I got my test statistic now and they didn't give me these two numbers. How would I go from getting T equals negative 3.95 to getting a p-value? Not inverse T, TCDF. So I would do TCDF of negative 3.95 to infinity. No, it would be negative infinity to negative 3.95 because it's negative. And then I have 9 degrees of freedom. So try typing this in your calculator. TCDF, negative infinity to negative 3.95, 9 degrees of freedom. Tell me what you get. I got 0.00167.
Yeah, that's what I got.
which is different than 0.003. 0.00167. Okay, it's different. And let me tell you why it's different. This is very important. So, p-value given in a computer output is always a not equal to. So, it's always a not equal to test. So, if I were to double it times 2, so in your calculator do times 2, then you get 0.003. So, something to take note of is like if it gives you computer output and it gives you a p-value, but you're doing a greater than or a less than test, then you're going to have to divide by 2. But if you're doing a not equal to test, you just take it as is. So circle that p-value and next to it put it is always not equal to, no matter what the test is. In this computer output, it always gives you not equal to p-value. So it always doubles your p-value.